Hey, Mr. Dean here. That we're going through part three, really, of a three-part series about how to graph rational functions. Here's the last one. It's graphing slanted asymptotes. In the certain case when the degree of the numerator is greater than the degree of the denominator. And check out this graph. The end behavior of this graph doesn't really approach any particular horizontal asymptote, as you can tell. It approaches this diagonal straight line. So we can have slanted asymptotes be straight lines. We can actually have slanted asymptotes also be curved asymptotes. So how about that? Let's get right into some examples here. So let's see here. I got this function and I want to first factor it. First step. So I'm going to factor out x, and it looks more like this. Let's see what information we can get out of here. I see that it has, just like all polynomials, it has the zeros of the numerator are 0 and 1, right? 0 and 1. Let's go find out the horizontal asymptote. Now you might remember that the horizontal asymptote doesn't exist. When n is greater than m, you don't have any. So none. Or no horizontal asymptote. Moving on, vertical asymptote. There is a vertical asymptote. That's the 0 of the denominator. You got to remember that. So positive 2. Now, anytime we do not have a horizontal asymptote, we can be suspicious that there is a slant asymptote. In fact, every time that n is greater than m, there is a slant asymptote. And it's easily found. It's kind of neat. What we do is we're just going to take this original problem, we're just going to think of that fraction as a division bar, and we're actually going to divide. And you can use long division, or you can use synthetic division. I'm going to use synthetic division here. And be careful. So we have a 1, a negative 1, and there's really a plus 0. We're going to go to the original function. We're not going to do synthetic division with this blue factored version. You have to go back to the original. And this is the first time we've kind of seen a placeholder down the end. But that's just okay. That's just the way it works. Just divide it out. So that's 1. This is a 2. This is a positive 1. That's 2. Cool. All right, so what we have is that this original function here, let me just move the factored version over a little bit. This original function is exactly equal to this. That original function is equal to x plus 1 plus 2 over x minus 2. All right, they're equivalent because we divided them. Well, we can say that as x gets pretty large, that the remainder part of this problem is not going to matter very much. It's just like this residual remainder, like the bottom of the Lucky Charms cereal box, right? As good as it is, compared to the whole entire box, it's really like nothing. So we're going to focus on a function really looking like x plus 1. So that is the slant asymptote. There is a slant asymptote at the straight line of x plus 1. And so there's going to be, if I've done this correctly with the scale, there's going to be a slant, let me just, slant asymptote right along that line. The y-intercept is 1 and the slope is 1. All right? So that's what the graph looks like. It looks like that diagonal blue line for the most part, except it's off by this little residual, by this little difference. That doesn't matter too much when x gets big. So we found that there's no horizontal asymptote. We have a vertical asymptote. Let's not forget about that. Vertical asymptote at 2. And now I'm ready to plug in some points. Don't want to plug in too many. Let's keep it simple. If I plug in 0, let's see. If I plug in 0, I get out 0. We already knew that. If I plug in 1, I get out 0. I knew that because those are the zeros of the numerator. If I plug in 2, I know that I'm going to get an undefined, because if I plug in 2, we're going to be dividing by 0. Let's plug in 3. If I plug in 3, I would get 9 minus 3 is 6 divided by 1. So I'm going to get 6. So at 3, I'm going to have a dot at 6. Point at 6. And let me try 1 over at, say, like, negative 4. Just to find out what happens when I'm way over here. Negative 4, let's see, we get positive 16 plus 4 over a total of negative 6. So I'm going to get 20 divided by negative 6. So that's like approximately, I'm just going to estimate, I know it's not exactly -3, but it's close. So I'm about here. All right, we have enough dots, enough points to draw our graph, believe it or not, because this top right graph, I know it's going to go in quadrant 1. It's going to follow along the asymptotes. It's got to. And these 3 points here, going to go, and it looks like it's going to just, has to kind of follow along those asymptotes. It has no choice. All right, as x gets really large, it's going to follow along that diagonal asymptote. And I look down here at my kind of cheat sheet, my calculator version of this, and yeah, there's where it turns, kind of neat, and it definitely follows this diagonal asymptote. Let's go to another example. 2x cubed minus 4x squared plus 3, all divided by, again, x minus 2. Well, the numerator is greater than the denominator's degree, right? We're 3-to-1 ratio now. And so we have no horizontal asymptote. We're going to end up with a slant asymptote. We'll get to that in a second, but let's not forget there's a vertical asymptote at 2 again. So let's go sketch my vertical asymptote right at 2 and the slant asymptote. So here's where I did the division already, synthetically divide. And we got that as an answer after I did it. And so once again, the remainder is going to go to 0. All right, as x gets large. When x is small, that remainder is kind of important, but as x gets large, not so important. So our slant asymptote is actually going to be a curve at 2x squared. So you remember what 2x squared looks like. I'm going to go quickly here and just approximate it. It's going to look like a parabola going through 0. And when I get to even as far as 3, 3 is going to be 18. So it's really, really steep. Notice my scale is very steep for this graph, because I kind of know, I knew what the graph is going to look like, so I set my scale up kind of funny like that. All right, so we have a slanted asymptote, we got a vertical asymptote, interesting. And then I've already, as you can see, I've plugged in a bunch of numbers, plugged in some simple numbers that will fit in. And I did know at 2, I didn't really have to plug that in because I knew it was impossible to plug in. But let me graph those answers here. So I plugged in 0 and I got out -1.5. So remember that green dotted line is the asymptote. I'm not going to be necessarily on that. 1 is -1, so something like that. 2 is undefined. 3, those rockets up to 21. All right, and -1, I just get +1. All right, this is going to be an interesting graph. I didn't quite leave enough room over on one side of it. But here are these 3 dots over here, and they have to connect. But what happens down here is that once you get to this 3rd one on the right, there's no choice but to rock it down. And you get this weird shape. This is going to follow along this green asymptote. Right? Rule of thumb is just follow along the asymptote. You can't go wrong. Now this dot here is kind of trapped between these 2 asymptotes, and it's going to be really steep. But that's all it can do, all right, in between there. Now I do need to know sort of what it does over here on this side. There's no graph. But remember, this asymptote goes kind of forever in that direction. In other words, if I were to plug in 5, I would have a value. It would just be way up, way up off the scale. So there isn't going to be any graph down here that we can see, because there really is a graph of it way up there. All right. So let's take a look at our graph. Yep, pretty much what we had. That's not bad. All right, moving on. It's kind of the end of the chapter there. Let's review a few of the problems. We've gone over all the different cases. Let's go back and kind of review. So to get your bearings straight, here's one where n and m are equal to each other. So just like everything, we have to factor first. All right. So this is where n is equal to m. Remember that case? We do have crossing out factors so that there is a hole, a removable discontinuity, at -2. All right? And I really should say at x equals -2. So we got, let's see what else. We got a vertical asymptote at x equals positive 2, right? We have a horizontal asymptote. Well, remember that? Horizontal asymptote is the ratio of the leading coefficients if they're tied. Well, they're tied. 2 to 2 is the degree ratio, is degrees, and the coefficients is 1. Let's see what else. Got the hole there. We could throw in some y-intercept. We kind of do that when we make our table, but just throw in 0, and it looks like you get 3/2. All right. And I know the x-intercepts, the solutions, 3, 0. How do I know that? That comes from there. All right, so that 3 comes from there. All right, we might need a couple more values before we finish our graph, but I want to see what the graph looks like and see how far I can get. Don't want to plug in too many values in my table. It just gets to be a drag. So I got my vertical asymptote at 2, my horizontal at 1. There's a little funny business here with the hole, so let's just remember that. And I'm ready to graph some of these. At 0, we're at 1.5, so we're above the scale there. There's an x-intercept right there. And yeah, believe it or not, I don't really need to make much of a table unless I'm a little worried about what it, I could make 1, we'll put in 1 here, and we get 1 minus 1 minus 6. So we'll get negative 6 over, let's see, 1 minus 4, negative 3. So I get 2. So at 1, we're at 2. And I kind of knew that, because it's going to be following along the asymptote here, and it's going to have to curve up like this. And on this end, it's going to do the same thing along the asymptotes. So I'm pretty much done with my graph. And I love it that I didn't have to plug in very much into my table. All right? Moving on to another one. Whoop. Whoa, whoa, whoa. Hang on. Number 2. Got ahead of ourselves. Factor out of 3. Don't forget to factor. Don't forget to factor, people. All right. The top does not cross out the bottom. Don't get crazy. It's x minus 1 and it's x squared minus 1. All right? But let's factor this completely. X squared minus 1. Anyway, as much as it doesn't factor like that, it doesn't cancel like that, x squared minus 1 factors. X squared minus 1 factors the difference of 2 squares. So there is a piece of it, yes, that will cancel out. All right? So factoring is super important. So there's a hole. Oh my gosh. I just remembered. Let's go back. I forgot the hole. I'm ashamed. Shame on me. Right there. Let's get that hole in there. All right. Hopefully I won't forget it on this one. Hole at x equals 1. All right, got to remember that. So what do we have left? After I cancel out those factors, just make sure that that's factored and canceled out. I got a vertical asymptote at x equals negative 1, right? This 5 does not create any kind of zeros there. Horizontal asymptote, well, they don't have the same degree, all right? Whether you looked at the crossed out version or not, factored version or not, they don't have the same degree. The denominator is greater than the numerator. The numerator is less than the denominator, in which case, as x gets really large, y just goes to humble 0. All right, nice. And let's get our graph going here. So I got this funny scale just because of the things get a little weird. Vertical asymptote at negative 1. Sort of like that. Horizontal asymptote at 0. Okay, a little strange. And let's plug in some values here. Let's plug in, well, if I plug in 0, what happens? I do get a value. I get 3/5. All right. 3/5. If I plug in 1, this is why I don't like plugging in numbers. 3. Oh, if I plug in 1, I get out a 0. Right. That was one of my zeros. I'm going to use a different color over there. Okay. Plug in, say, 2. Right? I can plug it into my factored version or not, doesn't matter. So I plug in 2, let's see here, I got 3 on the top, and I think 15 on the bottom. I think I did that right. So at 2, we're not very large, very small. Okay, let's go to like a negative number on the other side of the vertical asymptote. I know what it does at -1, it's undefined there. So at -2, well, it's going to be a little tricky. I think just to show you, I'll plug it into my factored version here. All right. So let's see, -2, -1, -3. So I got -9 in my numerator over, if I get -2, I get 4 minus 1, that's 3 over 15. What's important here is that I get a negative answer there. -2, I am at -9/15. All right. All right, pretty weird. Let's check out what the graph must look like now. All right. So it's going to, that little dot there, follow along the asymptote, follow along this asymptote. Nice sharp corner there just because of the scaling, really. And this one is going to come along this asymptote, kind of dip down and take off up the scale like that. All right, that's my guess on that one. Let's see how we did. Oh, I almost forgot the hole. Oh boy. So there's a hole at 1. So somehow, if I can erase there, right at that spot where we did have a value, there is a hole. So we can put that in there. And sometimes if you didn't make a very large hole, you think the teacher's not going to see that you did it, you get credit, put those words there. All right. Nice. One more example. This is going to be, we'll try to go quick through this one. Factor out a 3 and an x. Take note of that. All right. I factored that out. So let's take a look at horizontal asymptote. Y equals 0 because the numerator's degree is less than the denominator's degree. Vertical asymptote at the zeros of the denominator. There is 1 at 0 and there is 1 at 4. 2 of those. And I can start making a table of values. I can put my my y-intercept. I just throw in 0, but I can't throw in 0 because of that. So I get undefined right there. Because don't forget, there was a horizontal asymptote at 0. Vertical asymptote, there was 2 of them. All right. See if we can go through. Let's go put in a 1. And I will get, let's see, 1 minus 3 is -2 over 3 times -3, -9. So I get a positive 2/9. So at 1, I get a positive number, and that's all that really matters that it's positive. I know it's above the horizontal asymptote. I'll throw in a 2, because we want to know what's kind of going on in between there. So I'll throw in a 2, and I'll get -1 over 6 times -2, -12. So once again, I get a positive number. It's really small. I have a pretty good idea of what's going on in here. It is going to look like that. Let me pick numbers to the left of the asymptote there, the asymptote of 0, so I'm going to go to the left. -2 minus 3, -5. And let's see, -6 times -6, I believe. So I get a negative small number. So right about there. That tells me all I need to know. We're stuck in between here. Now I just got one more thing. I got to pick to the right of 4. Of course, I'll pick like 5. 5 minus 3 is 2. I'm plugging it back into back in there. And then let's see, 15 times 1. 2/15. 5 is above that horizontal asymptote. I believe it looks like that. Sure hope it does. All right, let's take a look. Aha! I missed something small. What happens is, this actually went through. Now let's take a look at what I missed so I can see what I missed now. I didn't miss it on purpose, but it is a good lesson. And And that is, I forgot about this 0, and one of the things I didn't plug in was 3. I would have known that. But there is a 0 right there at 3. So man, if I knew it went through there, I would have known that the graph would go down like that. But that's the only change I need to make. So I give myself an A- on that. All right? Thanks for tuning in, and we'll see you in class.